Hello everyone, this is Lorenzo and you're watching KSP to Mars episode 39, where today we're going to Venus, not Mars. First thing though is a little bit of cleanup. If we look here in the Space Center, we have 82 pieces of debris, and wow, the area around Kerbin has been littered quite a bit. We see here the Venus probe debris. Here's a bit of the Newgrounds launcher from like 20 episodes back. Luna 4 debris, I think that's leaving. No, it's not leaving, it's just on an elliptical orbit. And all of this is, I think, making my game a little bit slower. What I'm going to do is I'm going to postpone deleting anything that's in orbit, because, it's not realistic. But stuff that's on the planet, I'm going to delete that. So this debris is on Kerbin, to recover that. And this is on Kerbin, recover that. Oh, I think I double-clicked something. Yeah. Okay, let's see. These are the kinds of debris pieces that I'm just going to go ahead and delete. And there were 82 of them, so I'm not going to go through the list with you all at once. I'm just going to delete with you all at once. Gee, I really wonder where these words are coming from. I'm not going through the whole list with you step by step. I'm going to delete them to land at once, and then I'll show you the result in the list. So I'll be back in a bit. So that's not as much as I'd hoped. I managed to delete about 20 debris pieces, and now orbital space around Kerbin looks like this. And they all have wonderful ellipses going around the planet. Now I could go and check each and every one of them and see if they maybe have an apoapsis near the atmosphere, or if any of these probes that are here around Kerbin and everywhere in the solar system, whether they have any fuel left to maybe deorbit. Well, these ones might, but I'm not going to do that. I'm just going to soldier on, and well, I have 3 ships. That's actually not too many. The Kerbals are preferring to stay home. We have this one. This is actually a station now, but it doesn't have a command module, so I can't rename it. This is an empty vessel that will probably never be used, and this is the Luna 2 orbiting Kerbin. I don't know what this is, and we're not going to look at that today. We are going to go to our Venus probe, wherever that is, Venus probe 2, orbiting the Sun, fly that. And as we see here, the course correction is up in 29 days, and the maneuver node for that is, I think, stored by the Kerbal alarm clock. So we're going to test that out. I'm going to time warp forwards to that point, and you can see here the encounter is already set up. I'm going to just target Eve again, and I'm going to do time warp forward, and hopefully that maneuver node will then spontaneously appear. Now that I'm saying this, I remember that the maneuver node for the Venus probe was an empty one, just to set the point. It's the maneuver node for the Mercury transfer that actually has maneuver node info in it. So we'll just see if the system works now with the Venus node. That's going down to about a day. 10 more hours to go, and we shall see. We already have the encounter set up, just need to reduce the periapsis as much as possible. We need to wait a few more seconds, and hopefully, of course, this lander will be able to get through the thick Venusian atmosphere. And here we have it. Restore the maneuver node. Replace the maneuver node. Close alarm. Yes, I think... Awesome. Well, this is an empty one, but of course the maneuver node was an empty one, and I think that's just going to work for the Mercury node as well. I'm going to set this up and I will show you the result. Wonderful. With a maneuver node of just 30 meters per second, I've managed to change the trajectory into an impact trajectory. Now, of course, we don't want to do a straight impact, but well, that's going to be easy to modify into a grazing encounter as soon as we get into the sphere of influence. If we can make this happen, then well, we're in good shape, and we're definitely in good shape with this mission. I'm feeling confident. Now what I do with these maneuver nodes is I set them, then I lock the ship in the destination, remove the maneuver node, and then just thrust forward so I can fine-tune the periapsis. I might even be able to make it, let's do some memory. Last mission the atmosphere started at about 210 kilometers, so I'm going to try and put it for 250 kilometers. That way I can put the orbital part in orbit, and then make a controlled descent with the lander part, and maybe even aim it towards a specific landing spot as well. There we go, 230 kilometers, great. Quick saving that, and deleting the alarm, deleting this alarm, and the next alarm, of course, is the encounter for the Venus probe, 51 days. That's not the next alarm, it's the next alarm for this mission. And now we're going to move to the Mercury probe and alter its course, which is going to be a fair bit more involved. See, we're spreading out, even the inner solar system is getting crowded. Moho, let's set as a Mercury 2. I want to switch to that Mercury craft. Switch to it. So, there we go. So, here we go. This vessel has 10.8 kilometers per second of delta V left, which should be enough. I think past me put the maneuver node correctly so that it would encounter Mercury from there. Now, I've taken a few days break from playing KSP. It was just getting too much. I was playing for many hours a day making these videos. You won't notice a thing of that because I had a stack of like 8 videos in advance, so I took some days playing Don't Starve and other stuff. And of course going outside, reading a book, that kind of decent, responsible person occupations. But now we're going back to Mercury, and I'm going to trust past me to have made this maneuver node. So I'm going to have it restore the maneuver node and close the alarm. So let's see if that worked out. In fact, yes, it has. It's exactly the same as it was, and we will come upon that node in 2 minutes. It's a hideous maneuver node, 8.7 kilometers per second, and as I said, I think in the previous episode, is that this is about the most inefficient way to transfer to Mercury. It can't be good because, well, first we spent like 6 or 7 kilometers per second getting into this orbit, and now from this point, which is already fairly close to the planet, this is why it's so expensive. But we're coming in from a very much an off angle, and the transfer window calculator and alarm clock doesn't account for these hideous angle differences. And fortune or misfortune would have it that our ascending and descending node are really close to the encounter point, so there wasn't really a feasible way to change that before, apart from doing it now when we're really close, which costs a lot of delta V and is inefficient. Maybe I could have done it, but I just didn't cook up the right maneuver node. Here I am hunting for the blue direction indicator, and what I am hoping is that well, the solar orbit is large enough that it doesn't matter that this burn is going to take a while, because it is. I can just keep it pointed in the same direction and perform that burn. About half of it will be done with a nuclear engine, so that will be decently fast. But then we will switch over to the ion drive, which of course will be hideously slow. This is going to take a long time again. I will see you when that is over with. And there we are at nuclear stage burnout. We have 3.9 kilometers per second to go, and this rosetta of solar panels and heat radiators is slowly inching away from that stage. Can we still see it? It's too close to have a marker yet. I just wanted to show you it because it gives a nice perspective for how slow this accelerates away. And this is coming on top of the separation force from the separator. It was a tiny one, so not too much force, but this acceleration is not huge. If you look at the vessel display, we've got a thrust to weight ratio going on of 0.001. 0.001. Oh yeah, no, that makes no sense. It comes from the show Flight of the Conchords, and they have a part where they have they're doing a song and they do binary solo, and it goes 0.0000011110001. Yeah, I thought that was funny. Anyway, enough with the 0-1 ramblings. At this point, 0.001 thrust to weight ratio, of course, is a bit exaggerated because that's in relation to the sun's gravity, where I think even our heaviest booster would have a thrust to weight ratio of 0.001. Right, well, this burn is going to take 3 more hours, so I'm going to go ahead and accelerate that and see you on the other side. And there we are at the end of our burn. It took 3 hours and 45 minutes, accelerated 4 times, just under an hour. We have 1925 meters per second of delta V left, but that is irrelevant because we have an encounter at 13 kilometers. Now, I have to admit, much the spaceman I am, I don't really know for sure if Mercury has an atmosphere. I think it does, but it's really, really thin. But as I said, I'm not sure about this. I'm going to assume that the real solar system guy did his homework and that whatever we're going to encounter here is the real deal. And I know I said in the beginning of the episode that we were going to Venus, but look at the alarm clock here. We're at Mercury in 8 days, and at Venus in 39 days. So we're going to Mercury first with this probe right here. It's an 8-day time warp, which is otherwise known as a jiffy, so we'll be there really quickly. Let's trust the Kerbal alarm clock to slow down the time warp for me, which I'm really quite in love with that feature. Look at that, so precise. Wonderful. The transition will happen. Yeah, delete that node. And as soon as we're in the sphere of influence, which should be any second now, there we go, 13-kilometer periapsis, and we can do some science. It's been a while since we've been able to science things out about the, well, about the universe that we live in, or that these green Kerbals live in. We'll start with the magnetometer. Analyze magnetosphere while high in space over Moho. The solar wind seems to be being deflected. Well, that's good. Transmit that data. 96 points. That's a good start. And we have enough electricity. Well, we should, because we're super close to the sun. Look at that. Well, it still seems fairly small, but we're super close to it, and our panels are producing 2 kilowatts of waste heat, all of them. So that's really close. Gravity scan, 64 science only. That's disappointing. What else can we do? We can do a temperature scan, maybe? No, can't be done. Can we do a seismic scan? I'm thinking not. No, we have to be landed for that, obviously. We can have a look at the goo canister. You'll notice that we carry only one, and we have two science regions to science with that. So we're going to have a look at this. This would give me 24. We're going to keep that data. Oh wait, that's going to be hard, because 24 is not a lot. I'm going to guess that the close-in data will have more. With that said, let's time warp forward a little bit, but cautiously, because if we do immediately slam into the atmosphere, then, well, let's see if we can even spot the planet here. We will be there in 2 hours, so this sphere of influence is positively tiny. Oh, there it is. Hello, Mercury. Let's just for fun throw in a maneuver node here and see what it would take to get into orbit around this tiny planet. It would take a massive amount. Can you see that? We're at 3-4 kilometers per second, and it's barely even making a dent. That's of course because we are in a rather elliptical solar orbit, which goes out. Wow, this orbit is so strange. I had to spend like 10 kilometers per second to meet it from here, and that has pushed our orbit. No, actually, I was misreading that. I thought we were higher than Mars, which we're not. No, actually, our orbit is not that strange. It's got its apoapsis at Kerbin and its periapsis here at Mercury, and it's inclined. So no, nothing untoward there, but it would take a massive amount of delta V to get into orbit, because we are approaching the planet at 11 kilometers per second, which is only going to increase. And I'm guessing that, I'll tell you, I know, because common sense tells me so, that the orbital velocity for Mercury is not going to be so great. As Mercury is smaller than Earth, I think. Yeah, I'm pretty sure of that. It's smaller than Earth, so its orbital velocity is going to be lower than 8 kilometers per second. We're coming in from, what's our altitude here? 90,000 kilometers, with a speed that's already Earth escape velocity from sea level. So yeah, it would take a lot of energy to put us into orbit. So let's approach it. The beauty of this approach is, of course, that if there is an atmosphere, we're not going to leave any space debris. And if there's not an atmosphere, then we're going to make an amazing close pass, which should yield some nice visuals. Passing over the surface at 10 kilometers altitude, going at more than 10 kilometers per second. That should be good, I think. And let's see if we're in space near Moho yet. We are not. Let's time warp forwards to the point where we're at like 5,000 kilometers. I think that's a good point to check whether we are in a position that counts as near yet. Look, our orbital speed is barely changing due to Mercury. We've fallen 85,000 kilometers, and our speed has increased by like 200 meters per second. Oh, we can have a look at the gravity scanner, of course, to toggle the display. Look, from here, from 5,000 kilometers up, it's 0.37 meters per second squared. So it's quite a weak gravity field. That means that the orbital speed would be very low, and we would probably have to spend about all of this, like 11 kilometers per second, to get into orbit, or like 9, a absurd amount. This still counts as high space, so I'm going to next move to 1,000 kilometers. This is starting to look scary already. Remember, our periapsis is at 13 kilometers, so in space near Moho. Great. So we can transmit this gravity scan again, and we can transmit the magnetometer scan again. It's another 96 points. And let's have a look at the goo canister. Well, let's face it, we have to transmit it, because if we don't, then, well, the probe might die and it will be out here for nothing. This is also 24 points, so that doesn't matter. Transmit the data. And I'm going to have a look at the temperature thing, which I think does work near the planets. Oh, it will just tell me to toggle the display. It won't even let me log it anymore. So, is that broken or what? Ooh, we are falling really rapidly. Look at that. We're at 700 kilometers now, and it really won't be long until... I'm annoyed that I can't do this temperature scan. It won't be long now until we're very close to the surface. So, if I pull up the surface display here, it has our vertical speed as 7 kilometers per second. I bet that's the fastest crash, the fastest the fastest altitude diminishing, falling. I don't know what's the proper word in this circumstance. Vertical speed is a good term, I suppose. I think this is the fastest vertical speed relative to a surface that we've had in the game so far. Of course, if we count the probes, no, even if we count the probes that leave Earth, well, they would do so at like 12 kilometers per second. But even that is not completely perpendicular to the surface, so I'm not sure. It depends on, well, on whether this rock has an atmosphere or not, whether or not we're going to make it. I'm going to give up on that. Wow, it just looks like falling down, basically. I will remove the UI, and we can have a look and see if we are in fact going to make it. It's too bad it's sort of on the dark side, but not completely. Anyway, I'm out of profound things to say. Just going to watch this very expensive space probe hurtle towards the ground. Oh, one thing I'm going to check is to see if Mercury has... Ooh, the difference between terrain altitude... Oh no, it's really low. The mountains are not 13 kilometers high. Let's see if we're gonna make it. That would be awesome if we would. So far, I'm not seeing an atmosphere. We're still at 135 kilometers up. This is going so fast. We're going 12 kilometers per second relative to the surface. We are at 110 kilometers, 100 kilometers. Look at that. That's the surface. Is that a lake? No, it's just the planet texture changed. Oh, if there is an atmosphere, maybe we can do science in it. No. I did bring the atmosphere sensor. Atmospheric pressure scan can't be done. We're 50 kilometers altitude. Look at that. We're zooming along the surface. Surface reading, we're at 35 kilometers altitude. 30 kilometers over the terrain. Falling still at a kilometer per second. 26 kilometers over the terrain. I don't think Mercury has an atmosphere. We are going very, very fast though. Altitude is 18 kilometers over the terrain, 16, 13 kilometers over the terrain. We're still closing, we're passing over a mountain even. So we're at 10 kilometers over the terrain now, going really fast. Going at 12 kilometers per second horizontal speed, 9 kilometers over the terrain. That's just like one Mount Everest. Look at that, this is amazing. You're skimming the ground so close. Now we're rising again, gaining altitude at just under a kilometer per second. And I think we can conclusively say that Mercury, or Moho in the game, does not have an atmosphere, or at least is like less than... It could have an atmosphere that's like basically just rock outgassing. But it's like the vacuum. We could pass over that, no sweat, none at all. And there we are, saying goodbye to the planet, and we will spend just 2 hours and 45 minutes more in this sphere of influence. I'm going to accelerate time and see that recede in the distance. This is just 10 times accelerated. This is just 10 times accelerated. Look how fast we're leaving that rock. 12 kilometers per second, and we came within 9 kilometers of the surface. I think that's pretty good for a space probe. This is now defunct, and we can leave that behind. Right, on to the next one, the Venus probe. Oh, let's have a look at that. We only need to accelerate that forward for 30 more days, and then we can have a go at landing on Venus. Let's see, where is that? Where is that currently? The Venus 2 probe, here it is. We're going to switch to that and see about intercepting the purple planet with a thick atmosphere and clouds of sulfuric acid. Well, all we have to do really is just accelerate time. I'm going to remove these alarms. Just going to have to accelerate time for 30 days. This is something we can do. And there we go. And I think the node for Venus, yeah, that was at 226 kilometers, which is just about on the mark. I think that's when I'm in the sphere of influence, I'm going to increase that to 250, because I remember that we encountered the atmosphere last time at 200 something. And I'm pretty sure it was not 290, but it could have been 250. So if I'm going to go for 220, we could die. So yeah. That's first order of business, is to increase this periapsis. Oh look, we're passing behind the planet and then we're being pulled along with it. Right, so that means I want to use a maneuver node to set the correct angle. And setting a maneuver node is sometimes tricky. Okay, I want to do it like that. I just want to use this maneuver node to find the blue marker that gives me the direction, and then I'm going to inch along that direction and just look at the periapsis instead of using the maneuver node to, well, plan the whole maneuver. I'm just going to lock it with the SAS here, remove that node, and then just gently blip the throttle until this goes to, like, I don't know, 280 sounds decent. Sounds reasonable. And then let's put one at periapsis, a maneuver node I mean, and see what kind of delta V we need to get into an orbit around this pretty planet. We need a lot. We need quite a lot. 2 kilometers per second. Well, that's something we have, so we're not going to worry about that. And it's an 8-minute burn, so let's recap. We did all the science here in space, I think, last time. Oh, but I could have done that with the Mercury probe. Send it twice. Ah, gosh darn it. Or this. Oh, damn it. I could have done that with the others. Just send it more than once. It still works a little bit. So yeah, reminder, send stuff more than once. Great. So 1 day until the maneuver node, and that's incidentally also a point where we can resend some other science. I'm going to do more time accelerating. And then near... Ooh, this is really quickly. And then near Eve, where is that planet? We should be able to see it out. There it is. We should be able to do the science from here again. Oh, look at how wonderful that purple, soupy planet looks. Now, firing the engine. And let's take a look at our fuel tanks here. Oh, they're just starting on that one. This one is grossly overstocked with Delta V. This has 7 from now on, and we need only 2. After this, we really don't need anything. But, you know, that's good to have luxury. I was reading about the old Venera probes, the ones the Russians sent, and like I think Venera 4 or 5, they had a mission profile that was eerily similar to what inadvertently happened to the last probe. Basically, the point was the probe would enter the atmosphere, slow down, and deploy a parachute, and then drift down until the batteries ran out. or maybe they didn't so much ran out as they heated up so much they couldn't work anymore, because the Venusian atmosphere is at like something around 450 degrees centigrade, and that's a bit of a problem for electronics, because regular electronics, like the one in the computer you're watching this on, they are held together by things like solder and copper and stuff, and that melts at those temperatures. So Venus is not an easy place to land, and most landers, they have lifespans that are measured in hours and are limited by the temperature rather than anything else. Not power, not mechanical durability. Well, it is mechanical durability in a way, it's just not very durable because it's in a very, very hot environment. So it's an interesting place, that's for sure. Fortunately, here on the Kerbal planet, Kerbal universe, the problem is not so much with heat as it's just density. And I say just density, and realize that at the surface of Venus there is 93 bars of atmosphere. That's 93 times as much as here on Earth, and it's equivalent to about being under a kilometer of ocean. So actually, if you build your probe right, you don't need parachutes. You can just like sink through the atmosphere. And a nice metric, I got this from the KSP forums, where there's a few interesting discussions about Venus rovers and terraforming. There's a lot of idle, pretty random speculation going on, but there's some good numbers as well. And one of them is that like if there's a human and it's Earth gravity and there's 90 bars, then your terminal velocity would be 1 meter per second. So that's like slower than walking speed. So that's good. That's interesting. I like those kind of things. So let's accelerate time during this burn and see how we get on. I could cut this out for you. Yeah, and I am going to do so actually. So see you after this burn, where we'll find a place to deploy our lander and see if it fares any better than the historic Venera probes, and indeed our last one. So there we are in orbit, still burning, and in fact we're about ready to drop these tanks. Here, look at the map view. We are in orbit, and I want to land in this bit of area. There's a big landmass here, but that's in the dark, and I want to land in the light side so the solar panels can function. And I want to get my apoapsis down as low as it will go. Well, it will go as low as I thrust it to be, of course, while keeping my periapsis here about roughly this area. So I'm thrusting towards the planet, which might sound counterintuitive for raising your periapsis, but if you just passed it and you're thrusting into the planet, you're basically burning anti-normal, which will raise the periapsis while dropping the apoapsis. You're still burning mostly retrograde, but instead of just slowing down, you're also shifting basically orbital energy from the apoapsis to the periapsis. Doesn't really make sense because orbital energy is the property of the craft, but you're changing the shape of the orbit. Not all the energy is spent into changing the semi-major axis. Some of it is also spent in, well, modifying the shape. I don't know how better to explain that. Anyway, I'm shooting for a roughly circular 270-ish kilometer orbit, from which I can then enter the atmosphere. And well, as soon as I enter the atmosphere, it will be pretty much a case of slowing to a crawl pretty quickly, because this atmosphere is so gosh darn thick. So what I might do is leave it like this, actually, contrary to everything I've been saying so far. Leave it like this, and no, I'm going... don't know what I'm going to do. I'm going to go ahead and reduce this. Although there's not really a reason to. I might just... my periapsis is here over this lake. I definitely don't want to end up in here. I want to enter somewhere here. So now with this shape being a little bit more curvy, the problem is if you're coming in really fast, the apoapsis is also like the only point where you're actually near the planet. But now because the curve is hugging the planet a little bit more, if I drop the apoapsis here, like well into the atmosphere, I'm actually going to enter here somewhere. So if I drop the apoapsis here at the end of this plate to, well, let's call it 150 kilometers, then I might enter somewhere here, which would put me over land. Or I could just do it here and land in the dark and deal with that. Or I could just slow down now and enter here, but that would probably put me over this peninsula region. That's not something I want. Damn it. What I'm going to do is I'm just going to chicken out and zoom about for a whole lap. Oh no, wait, I'm under 200 kilometers now. This is not good. I need to put the orbiter higher. No, that's not good either. I need to put the orbiter higher because I want to keep that in space, obviously. Not that it's going to serve a purpose. It's nice to have an orbiter and tell people I have an orbiter around Venus. But yeah, so restore that to 250, and then now I'm just going to switch to the other craft because I am done finicking around and just want to make something happen now. So final systems check before departure. Is the battery charged? The battery is charged. Okay, we can depart. This is the right decoupler to separate. It is. Throttle is at 0. All good. Separate. There we go. Switch to the other craft. Here we have everything we need. We have antennae. We have deployable parachutes. Some redundant heat shields here. Well, heat shields are solar panels, and of course we have these deployed solar panels and the, well, as I said, the titular heat shield. I'm just going to separate from the other craft here. I should do it. Enough separation. And then it's a matter of moving on to the apoapsis and lowering our orbit. Or I could do that from like here. A periapsis of 7 kilometers. That sounds somewhat daring. A periapsis of 100 kilometers here, while the atmosphere starts at 200. Yeah, I can work with that. Let's try that. A little bit more periapsis. Because at 120 I'm basically going to stop dead. Yeah, I'm going to go with this, and I will probably enter the atmosphere somewhere here, which is exactly what I want. I can deal with G-forces here, because, well, I'm a robot, not a Kerbal. So as long as the heat shield is fine, I should be okay, and I think it will be because the orbital speeds are not excessive. And I don't think the G loading will go over like 20. I have no idea what the parts can stand up to. Oh man, this Kerbal alarm clock is so good. It will slow me down automatically for maneuver nodes, for planet intercepts, for anything I want. Oh yeah. This pod is upside down, so that's always nice when you build your rockets upside down. The nav ball will be all crazy. So, right, here we are. What does our trajectory look like now? We have a periapsis of 128. We're just going to go with that. Let's time warp forward to that point where all the engineers yeah, no, I don't want this. Close the alarm. All the engineers that built the probe are dreading the moment because they're afraid. They're pussies and wimps. We have a full electric charge, well, almost. And before we hit the atmosphere, of course, we are going to retract our solar panels and work on battery power, of which we should have enough. Look at that nice and colorful sunrise. You want to bet like $1 million that I'm going to land exactly in this spot? Not on land. Right. Time to retract the solar panels and make our atmospheric entry. And of course we are oriented the wrong way around, which is something we don't want to be. We want to be oriented with our heat shield pointed into the atmosphere. Right, so there we go. I'm going to reorient that using the reaction wheel. The mass distribution of this should be enough to... Oh dear, oh dear. Okay, it has begun. I thought we were way over the land here, but that's just because this planet is so large. That's real solar system scale dysphoria. I thought this amount of distance would correspond to this amount of distance, but of course this is thousands of kilometers. This will be fine. We will be fine landing here. Decelerating at 1G now. 1.7. Let's have a look. 1.7. Time to impact. It doesn't tell me yet. Either way, I'm going to try and peer through the blaze here and do a pressure scan. Let's have a look. Log the pressure data. No, can't be done. It's being incinerated. So our electric charge is doing good. Our shielding is doing good. Our G-forces are doing good. Let's have a look at that. 670 degrees. That's almost nothing. We are happy and doing well. G-forces are increasing rapidly now. Maybe we can have a look at the readings from the atmospheric sense. Oh no, what's that? What the hell was that? Kerbal engineering system. Oh, yeah, that was mounted on the outside. So no more... Ooh, this is burning up everything. Yeah, no more readouts on G-forces and delta V and that stuff. So yeah, I have to do without that. Toggle the display. We're... Oh, this is not... We're at 1 millibar at 170 kilometers. So that counts as outer space around Earth. This is the 1/10 of the sea level pressure of Mars, but instead it's 170 kilometers up here on Venus. So that's awesome. Log the pressure data. Wow. 36 science points. I'm going to try the same as I did with the last probe to save this data and then transmit it once we're in the gliding phase of the entry. Well, I suppose this counts as a gliding phase as well, but the phase where we're not burning up everything that sticks outside the fuselage. So 3 kilometers per second left to scrub off. We're going at 6 Gs more or less, and still slowing. Oh no, this is actually decreasing, so we are decelerating the deceleration, which is good. That means we're through the thick of it. And that was a very intended pun, and we're definitely not through the thick of it because we're still plummeting into the thicker parts of the Venusian atmosphere. And the thicker the atmosphere, the more your shield ablates, because even though the speed is lower, you're shoveling more mass out of the way, so it's really best to do most of your slowing down at relatively high altitudes where the air is thinnest. No matter though, our shield is, ablating away, but it's only 400 degrees now, and we are traveling at only a relatively sedate kilometer per second, so we should very much be fine. And that means that now has come the time to transmit that precious pressure data home. So let's do that and transmit it. And maybe we can do a temperature reading as well. And the beauty of this system, of this new and revised probe, is that we can transmit with abandon, because these solar panels at the top here, they will give us electricity. The batteries, they will last forever. And even if we do run out, these ones are there to give us electricity to deploy the parachutes and to later, when we're landed, deploy these deployable solar panels, which will give us, well, electricity forever. No gravity scan. Where is my thermometer? Are you telling me I didn't bring one? Eve's upper atmosphere. Temperature. Yes. Transmit that home as well. So right now we're just emulating the Venera probe, sending home data while falling, although sinking really is a better term, while sinking through the atmosphere. We need to disable the SAS system, and you can see that I even designed this correctly. It's orienting properly along the vector, where even if I did not do the SAS module, it would have had the heat shield in the heat. So I'm happy with that. Well done, past me. Yeah, now there's really nothing to it than to wait until this has landed. Can we have a look at the atmospheric pressure again? We're at a tenth of a bar at 90 kilometers altitude. That's what counts as the boundary of space, is the Kármán line on Earth. We defined that as being space, and it's not the point where there's no atmosphere, but there's definitely less than a tenth of a bar. Right. I will fast forward time a little bit because I have a feeling this is going to be a very tedious and very long-lived re-entry. Well, entry. So see you in a bit when we're closer to the surface. Oh, in my enthusiasm to, well, stop talking, I forgot one of the science experiments that's, well, magically floating on the side there. We brought a gas chromatograph to tell us the atmospheric composition, so let's do that. It calls itself the magnetosphere, but high in the atmosphere of Eve, clouds of sulfuric acid can be found. I have a feeling that's the start for a poem, but it's not really rhymey. So, anyway, let's transmit the science. And after this landing, we are definitely doing a trip to the R&D station because I think we are getting a lot of science points. Well, I know. So, we got the data, and let's do the spectrometry results here. Let's have a look. Analyzing. Gee, that takes a while, that analyzing. Can I have a look at the temperature in the meantime? It's minus 40. Yeah, this temperature system really doesn't work so well yet. %10 more to go on the analyzing. I'm quite curious what it comes up with. Carbon dioxide, nitrogen, and argon. I have a feeling this is just incredibly random because I think I know that Venus's atmosphere is like almost completely carbon dioxide, like 95% plus. But then again, I'm not absolutely sure about that. I have a feeling there's too much nitrogen in here. Anyway, this is what this tells us, and here Eve, stand-in for Venus, has a 36.54% nitrogen atmosphere, because why not? Right, I'm going to do as I promised and be back with you when we're landed, or at least in the lower atmosphere, so see you then. So we're now at 37 kilometers, still not quite close to the surface, but I thought I'd take this opportunity to show some nice things that Ferrum Aerospace does for the game. It's a mod that makes the parts behave more aerodynamically valid. It improves the stock aerodynamics model by a great deal. And now that we're in a thick, soupy atmosphere, things move very slowly, and you can easily show this. Just to have a look here, let's have a look at the pressure. We're at 5.5 bars already, and we're just sinking at 37.5 meters per second. This is our terminal velocity for this vessel and its orientation. Now the fun thing is, and this is not modeled in the stock game, if I turn it on its side, and I need the fairly powerful reaction wheel to do so, because aerodynamic forces would want me to not be in this configuration. But look, we have a larger cross section, so we have more drag for the mass of this probe, and our speed now has dropped to 22 meters per second. Now this is in effect on Kerbin as well, but it's not as well noticeable because everything happens much faster, and because the speeds are so much higher. If I were trying to pull this off, the force would be too great. Either the thing would be ripped apart, or the reaction wheel would just not be strong enough to sustain the position like this. You can see when I turn it off, aerodynamic forces, they act on this whole bit, but this area is a bit lighter than this one, so this will be pushed up higher than this, and that changes the cross section. Apparently this is now the new stable form, but if I use the reaction wheel to put it upright, then upright becomes a new stable form. So this isn't so important for making rockets, but when you're making planes, this is a much more realistic way of calculating things. And well, while I was waiting through this tedious drop through Venus's atmosphere, I thought I'd show you. So let's have a look if we are in the lower atmosphere yet. No, we are not in the lower atmosphere yet, so I'm going to cut out again until we are lower still. See you in a bit. And here we are, after almost half an hour of sinking through the atmosphere. We're finally coming up on the surface. We have 5.8 kilometers to go, although this could be a platform that's a bit higher. Well, a plateau is the proper term for a higher area of geology, not a platform, I don't think. I did all the lower atmospheric science, that all went off without a hitch. Look, 0 to be gained by transmitting. The pressure is very high, even at this altitude. Yep, let's have a reading. It's 38 bars now. So I wonder what the game has it at ground level, if that would be the full 93 or perhaps something else. Now, I did most of this descent without time acceleration because I'm afraid of the parachutes deploying under time acceleration. I've not deployed them as yet, but they're going so slowly now, just 14 meters per second without parachutes, that I'm going to do the time acceleration and then just when we're near the surface, just deploy them from there, so that they might immediately go from the parachute container to their full deployed state. I think that ought to work at any rate. Work better than have them deployed and then snap open at time acceleration, because this is going to take a long while still, even though we can clearly see the ground. So I hope we can do a landing without any parts exploding, because then we should be able to return a treasure trove of science from this very flat plane of Eve's surface. Of course, I mean Venus. Excuse me, my apologies for that misnomer. Here we go, and I'm going to reduce the speed as much as I can before opening the parachute by, of course, going sideways as I demonstrated before. So let's do that. And by lying on our sides in the thick atmosphere, we have reduced our speed to 7.9 meters per second. And with that, I'm going to deploy the parachutes. Look at that. That's a heat shield. It's just like fluttering down. That looks so funny. Look at that. It is just like that heat shield is dropping down ever so slowly in the thick atmosphere. That's nice. that's amazing. Look at that. Oh, and if we go like this, we're actually catching up on it. Look. Oh, and then we can go sideways again, and then the heat shield goes faster. Oh, fun with Farum. Look at that, pointing down. This is the most aerodynamic shape, of course. And now we go sideways again. Did we even deploy the parachutes? We did not deploy the parachutes. Let's do that. By heat shield. Oh, of course, because when the heat shield separated, it focused on that, and then the look, it's so, I don't know, for some reason I find that flopping heat shield incredibly hilarious. I don't know why. We can tell how far we have to go, of course, by this. 173 meters. Wow, that's a fiery explosion even for that. What, did one of our parachutes fail? I think it did. No. Yeah, it definitely seems as though one of our parachutes failed, although both icons are green and this one appears fine. We're now descending at 0.8 meters per second. I think that's a safe speed to touch down, even though we're using our SAS module as a landing foot. Yeah, that should be safe. Maybe even in time acceleration, although I'm not going to take that chance, obviously. This is how thick the atmosphere is. Let's have a look at what our atmospheric sensor has to say about that. 48 coming on 50 bars, and that's at 2 kilometers. So it might even be the full 90 bars at sea level. But yeah, no way to check that because, well, we're not landing there. We're landing here at 0 times time acceleration, and I'm going to use the SAS module to have us land completely standing straight up. This is how thick the atmosphere is. 0.8 meters per second. That's amazing. And that heat shield was just, it was, I don't know, too much. It was hilarious. I think it's time I go to bed. It wasn't that fun, but it was really fun. I had a great time with the heat shield. Did you have a great time with your heat shield? If not, call us now on 0900. Well, ugh, never mind. Here we are. Touchdown, soft landing on Venus. And let's first deploy the parachute. No, not the parachute. Jesus, the solar panels. This is how this lander is supposed to function. Wonderfully. Extend the antennae. Just because we can. And it's going to have to transmit a lot of data from the surface of Venus. The materials bay, there we go. The crushing pressure of the atmosphere is causing some of the materials to crystallize rapidly. Great, only 40 points though. That's disappointing, but there we go. Can we do a gravioli experiment? Yes, the gravity field is very strong here. The sensor records detailed data about the local field. Wonderful. Transmit that. Can we do... No way! We forgot the magnetosphere data again. But I think that doesn't work in atmosphere, so I'm going to get away with that. We do the spectrographic data from here, 60 points. And this sensor has to be done twice for some reason. The atmosphere of Ethene consists of carbon dioxide and nitrogen. Great. So more science from that. And of course from the temperature reading, 32 from that as well. Temperatures range between very cold and hot enough to boil water. That doesn't make any sense. It does not. Right, moving on to the press sensor. 48 for that. It crushes down on the instrumentation. Yes, it does. And I think that's all the science we can get from this probe. But even if it's not, doesn't matter, because it's safe and sound. We can return to it if we so please. So that's that for now. Let's return to the Space Center and have a look at our research and development center. And with that, if we do take a look at that, I'm going to end the episode after that, because even though I didn't intend to, I have a feeling it has become quite a long one again. We did probes for Mercury and Venus and some transfers in between, some rambling in the beginning. Yeah, this is going to be a long one again. 966 science points, going strong with that one. I forgot everything I said before on the previous episodes. We can't do this. This is 1,000, but it's good. I want this Deinonychus engine. We can't do this. This is 3,000. We can do this. This is 550, but it doesn't have anything that I want, so I'm not going to do that. I could do this. This doesn't have anything that I want. This doesn't have anything that I want. This does have stuff that I want. This has the phased array microwave transceiver, and that allows us to beam power to distant places that they can then receive the power and drive a plasma thruster, which is amazing. Rover wheels, I don't want that. Particle accelerators, antimatter collectors, I don't want that yet. And 2000 science. I'm going to go ahead with the phased array transceiver stuff, because that allows a new generation of spacecraft, and after that I'm going to shoot for these bigger rockets. So let's go ahead and get this. We have new toys to play with for the next episode. Check back for that tomorrow. For now, I've been Lorenzo. Thanks for watching. Click like, share, enjoy, comments, subscribe, all those things, and I'll see you next time. Goodbye.